Good morning, everyone. In this video, you will be learning about degenerate conics. Let us recall the general equation of a conic, which is given by ax squared plus cy squared plus dx plus ey plus f equals 0, where a, c, d, e, and f are all real numbers. We can also represent a conic using two cones and a plane that may intersect at least one of those cones. And we have a parabola, ellipse, and a circle, and a hyperbola. Let us ask ourselves, what if the plane intersects the cone at the vertex? If you can see in the figure, you see that the plane here intersects the two cones along with the edges of the cone, and it actually forms a line. For this one, we have a plane that intersects the cone, but exclusively at the vertex. And with that, we see that it results to a point. Meanwhile, if the plane intersects the two cones at the vertex, but is perpendicular with the base of the cone, we see that the intersection forms two intersecting lines. One that starts with a line that starts with the back portion of the bottom cone extending to the front portion of the top cone. And the other starting with the front portion of the bottom cone extending to the back portion of the top cone. Consider how we could come up with these results algebraically. Let us begin with an ellipse. We say that the general equation of a conic is an ellipse if the product AC is positive. That is, A and C have the same sign. So if we consider this, we could actually come up with the standard equation given by these equations, which you have already learned on the second week of our classes. These set of equations tell us that an ellipse is a set of points, a set of coordinates that can satisfy these two equations. So basically, in other words, for a point to be a member or to be a part of an ellipse, it should satisfy these equations. What we have observed is the following. This equation, this standard equation, must be equal to 1. If it is not equal to 1, then we should come up with a technique or a strategy to make it 1. The very basic technique to deal with such kind of equation is to divide everything by the number that is found on the right side of the equation. For example, in this case, it is equal to 7. So we need to divide the whole equation by 7. Doing so would result now for the right-hand side to be equal to 1. Again, it is also a must to make sure that the coefficient on the left-hand side of the equation to be 1. As you can see on the second equation, the terms x plus 1 quantity squared and y minus 4 quantity squared has a numerical coefficient that is not yet equal to 1. To do that, we have to bring it down on the denominator of the fraction, and that results to 7 over 3 and 7 over 2 respectively. Now you can see that the original equation actually describes an ellipse. Now let us observe when the general equation of an ellipse, after being manipulated algebraically, turns out to be of this form. Instead of equating to 1, it turns out to be equal to 0. What kind of a conic is this? This turns out to be a point. Now, why is this a point? Let us investigate the equation. The left-hand side of the equation are two terms that are being added together. Now, these terms, if you would observe, are terms that are squared. If a number is squared, we know that it should result to a non-negative number. It is not possible for a real number to be a negative number when squared. If you have two non-negative numbers that are being added together, turns out to be 0, it should be the case that the two numbers are both 0. It only means that the only coordinate that can satisfy this equation is the point hk. Hence, the set of points that we are looking for is just composed by a single element, a single coordinate, namely hk. Hence, we have the first degenerate conic, which is a point. Now, having the same argument, if the right-hand side of the equation turns out to be a negative number, then it is actually an impossible thing to happen. Why? Because the left-hand side, again, are terms that are non-negative. Adding them together must result to a non-negative number as well. Hence, to get a negative 1 or any negative number on the right-hand side must not be possible. Thus, the second degenerate conic that we are looking at is an empty set. And those are the degenerate conics for an ellipse. For the next video, you will learn about the degenerate conic related to hyperbola and parabola.